I'm going to recapitulate a bit what we started doing yesterday. And Anirban asked me if I can go over one of the examples step by step. So it will also be recorded. So if someone afterwards wants to repeat the steps, we can do it. We can do it that way. So these are the slides that I showed yesterday last. I showed what are the input and output files that are required for the code to run. They are the initial texture, the file with the crystal file with the active sleep and twin systems and the hardening parameters, the boundary conditions, that is the type of strain that you want to apply to your crystal. And as an output, there is this run logout file that has the information about the run, the texture file, the stress strain file, the activity in the sleep in twin systems, and eventually there may be, if you ask for, a polycrystal yield surface file and the LAM4 file. We are going to see today what they look like. We are doing an example later for rolling. So I already the main input file, which is the bpsea.in, and this file contains the files that you are going to be using and contains the information about the parameters of the run, contains the parameters of the run that you are going to be doing. As I said, the ones that are most relevant, the ones that are more relevant are the ones indicated in red there. The texture file, the single crystal file with the parameters and the sleep and twin systems, and this is the strain history that you are going to be running, or other processes that we will discuss later today. We said we are going to look first at example 2, which is tension and compression of an FCC polycrystal. There is only one sleep system here, the 110 Burgers vector on the 111 crystallographic planes, and we are not putting any hardening. The hardening law is rigid, perfectly plastic, where only tau 0 is equal to 1, and the imposed velocity gradient is this one, tension in the direction 3 with compression or lateral strains minus 0.5, and this is a rate. And then I mentioned that we are going to go into these two sub directories: tension extrusion, compression extrusion, and we are going to get the VPSC file from those. They contain also the output files. You can compare what you get with those. And what I was asking you to do is to compare textures and sleep system activity against those, or just plot them and see what happens compared to what we show here. How many of you have run these examples? Okay, so I'm going to go a bit over them again. And here I suggested that if you put hardening in the law, so maybe you make theta 0 and theta 1, give it a slope to the hardening curve, that the result for the texture and for the system activity is not going to change, because that is a kinematic condition, and no matter how much the grains are hardening, you are imposing the strain to the grains, so they really have to use those systems, whatever the critical stress is, they have to use it because you are forcing that. And then I was also suggesting that you test or check what happens if you suppress grain reorientation or shape orientation and compare results. I don't know, has anybody done that last suggested exercise? Okay. I'll leave it there for you to do it whenever you want or can. Then we're going to be running this texture. I also suggested that you use POL8 to plot this texture, just to make sure that you can get that result and you get more familiar with POL8. The process is, as I said, an extrusion process. In this case, all the components of the velocity gradient are fixed, and that is what this label or tag indicates is that each of them refers to each of these components of the velocity gradient, and all of them, the one is that the component is imposed, all of them are imposed, and of course then the Cauchy stresses are unknown. The Cauchy stresses are going to be a consequence of imposing those strain rate components, and that's why the label for the Cauchy stresses are all zeros. These are integers, these are the Cauchy stresses, and the code has several checks. Yes, of the velocity gradient and the strain rate. Why don't you ask
So,
again so everybody can
yeah,
hear?
all the components of strain rate tensor or velocity gradient tensor are enforced in this case.
Correct.
Then what is that ICTRL enforced component in the first row?
Which one?
In the first row, one ICTRL, the second, in the first row, that tree.
Okay, I'm coming now to explain this. Yes. What I was going to say is that the code has internal checks. So if there are inconsistencies in the way that you enter this data, the code will tell you, for example, you cannot impose epsilon 11 and sigma 11 simultaneously. So if the number here is 1, the number here has to be 0 and vice versa. So the code checks for some inconsistencies when you're imposing boundary conditions. So you cannot impose a stress component and a strain rate component in the same direction. It's either one or the other, and one is the consequence of the other. So what we are going to be doing here is we are saying, okay, we are going to make 50 incremental steps applying this strain rate. We are going to make 50 incremental steps. We are going to be imposing the component 3. The component 3 is, in void notation, is the component sigma 33, as I showed yesterday. The void notation assigns 1 to this component, 2 to this component, 3 to this component, 4 to this component, 5 to this component, and 6 to this component. So if you impose sigma 12 or epsilon 12, you are going to be imposing the component 6. You get the gist. Okay, so we are imposing a component 3, which is, this one is, let's say, 1 per second. As I said yesterday, the units are arbitrary, but they have to be the same throughout all the parameters that you enter. And this is the increment of this component that we are going to impose, 2%. So 2%, so we know 2% for this component, we impose the strain rate. So that allows us to calculate the delta T using that equation. And then the temperature in this problem is not an issue because there is no temperature dependence, but it is there for other problems. So is that okay? That answers your question. Thank you. Then the single crystal file, and you have probably seen it because the files are available to you, but it looks something like this. I have cut it here because it's too long, but essentially the first part gives the characteristics of the unit cell, so the length of the axis A, B, and C of the unit cell, and the length of the axis is in also, what matters is the ratio of them. It doesn't have to be 3.2 Armstrong, for example. You don't have to give the real number, you just have to give the real ratio between the unit cell axis. And then the angles between the axes. For the cubic is a very straightforward one. Then there is elastic stiffness in the thermal expansion coefficients, which are used in the thermoelastic option of the code. And then there is a list of what are the active slip and twin systems. What are a list of slip and twin systems, which is the number of modes here. In this file there were 2 modes, so there were 12 slip systems and 12 twinning systems in this file. Of course, I cut them here. And then you have to say how many modes are you going to use? Only one. And what is the index? And this is the index of the mode that you're going to use. So the code just skips the ones that you have not selected and picks the one that you have selected. Maybe tomorrow or when we do the example for zirconium, this will become more apparent how you work with these parameters. And then after that, there is a constitutive law for that for this material. In this case, the constitutive law only has information about the sleep systems, 111 and 110, because that's the only one that you use. So you put a power n here for the n sigma over tau to the power n, which gives gamma dot equal gamma dot 0 m sigma over tau. So you give this n. By default, this gamma dot 0 is equal to 1 by default. But one can change it, or it changes if you use the option that you are not going to make it rate sensitive the problem, in which case as I said yesterday, if gamma dot s, if you impose a large strain rate, you will need to increase the value of sigma here in order to get a larger strain rate. But if the strain rate dependence is here in this, in tau, you want that to be the one, the dependence, and not the one that comes from having this power law. So in that case, when you use array sensitive equals 0, so you don't want to eliminate the effect of this, the gamma dot 0 gets defined equal to the norm of epsilon dot. And it is easy to show that in that case, the stresses are all the same. The stresses are all the same, independently of what is the strain rate that you apply, because this grows with the strain rate, so the stresses are all the same. But the dependence then will come from, if there is one, it will come from this tau. I mean, you can try these things. You can try enforcing say minus 0.5, minus 0.5. Well, not with the n1 as the velocity gradient, and then multiply this by 10 to the 3, or multiply this by 10 to the minus 3, and run those cases and see what changes in the runs that you make if you choose the rate sensitivity 1 or rate sensitivity 0. You will see that the stresses, not for this problem, because this problem doesn't have hardening. Yeah, there is going to be a change, yes. And then there is the latent hardening. The latent hardening are these coefficients here, HSS prime. In principle, for this subroutine, they couple different modes. So if you have a basal sleep and pyramidal sleep in hexagonals, they are the ones that couple basal sleep with pyramidal sleep, basal with basal, pyramidal with pyramidal, and so on. So they are coupled the most, but that is not a limitation, because you can couple different systems too. But in order to do that, you really have to go inside the subroutine and change that. I mean, if there is a need, one can do it. If you know how to couple different sleep systems instead of different sleep modes. And then I show you these results, which are obtained for all the possible interaction assumptions between the inclusion and the medium. As I said, the Taylor and the secant assumption it correspond to a medium that is very stiff, meaning that the medium is going to force the inclusion to do whatever the medium is doing. So there is going to be no dispersion in the strain between the inclusion and the medium. The other assumptions, like the tangent here or the fin, are characterized by a medium that is more compliant. So if the inclusion is harder than the medium, is going to deform less. If it is softer than the medium, is going to deform more. So that has to do with the interaction assumption that you take. What we said is we were going to do a secant and the tangent, I think, yesterday, and check the differences. The differences are these. You have to get this or that. You have to get this or that, depending which one you use. So you will check that you get those results. And then these are the textures that you obtain after 100% tension and 100% compression. And I described it yesterday, said that for stiff interactions you get two clear components, one with the tensile axis aligned with the 001 direction of the grain and another with the 111. But for the more compliant assumptions, you get a spread here. It's not so clear cut that you have those components. And in the case of compression, you get a spread here when the material is, the compliance is low, the material is stiff, and you get more of a concentration when you don't. So this is the cases that we are not going to run all of this, but that is what is suggested to be done. What I will try to do now is show the different steps that you will have to take in order to run the code. So you will have to go to, you have here VPSC8 and then example 2 FCC, and in this example I can't remember what it is called, but it's probably called tension. We are going to see now, or compression. So this is example. Compression extrusion and tension extrusion are the compression extrusion and tension extrusion are the directories, but the input file for this problem is not in those directories, but in the example 2 directory. We are going to pick BPSC8, let's say compression 2. We are doing compression, so we are going to be doing compression, and we are going to be picking the file that is in this directory, which is VPSC8 compression2.in, and you will rename this file VPSC8.in. VPSC8.in. And move it and move it to that directory. So the case 2 is the secant. This is the secant case. This is the secant interaction. Yes. Okay, then I assume that everybody has compiled the code and has the compiled version of the code here.
What does 5 mean? The interaction 5.
Oh, 5 is, I'm not even going to describe that here in this course, but it's a second order. I mean, it's an interaction where in the linearization you use fluctuations to get, and I think we were discussing that yesterday, the second order with you, where you take into account for doing the linearization deviations that are calculated in an ad hoc manner, and so in principle that allows you to get not only the stress in each grain, but also standard deviation value for the stress in the grain. The theory is rather complex, and the run times are much higher than the ones that of the other cases. So I don't think it is worth really getting into that. You try with the input files that okay, we can discuss that later. The input file should work for that case, but let's look at it. So what's next is then I go to into the root directory, open the command window, and from the command window I run BPSC8. So we are going to be running a viscoplastic simulation. I think I will try to include a thermo elastic simulation for you to see how that is done. So you choose the viscoplastic simulation, and then those 50 steps. As you can see, it runs very fast, and it gives you here the information on. There are three criteria for convergence in the code that have to be met simultaneously in order for the increment to be accepted and pass to the next increment. And those criteria are. Do you remember yesterday I said that there are two nested loops? In this nested loop, you calculate the m, and in this nested loop you iterate over the sigma in the grade. Okay, so you will start with a sigma g n, and at the end of this step you will have a sigma g n plus 1. And then you check if sigma g is equal or very close. So you check if sigma g minus sigma g n minus sigma g n plus 1 square sum over all the grains is lower than the tolerance. You read this tolerance in the file BPSCIN, and if it is lower, that means that your iteration has been successful as far as the stresses are not changing anymore. What you guessed here, your guess here, when you recalculate the sigma here at this point, coincides with your guess. And then that is one condition. The other condition is that the norm of the epsilon dot average has to be minus the sum of epsilon dot in the grains by the weight of the grain. This also has to be lower than the tolerance, meaning that the average of strain rate between the grains is equal to the value that you are imposing externally, and the same for the stress. The macroscopic stress has to be minus the sum of the stress in the grains, has to be lower than the tolerance. So the average of the stresses, the average of stress rates is equal to the macroscopic one, the one that you impose, and the stresses in the grains have converged. So those are the three criteria that you see in this file. Those three numbers. So it gives you an idea of how the code is converging and in how many steps. This number is just the number of steps it took to converge. Okay, so what we have here is essentially this bunch of output files, and the ones that and you may want to look at I mean the stress and strain file I already explained it yesterday. We can look at it again. The texture file is the output texture. We can plot that texture to see what it is. For example, I can run polate. So I give a label of 5 characters. Oh no. Oh, because I don't have the right single crystal file. Okay. Okay, I'm going to change that here so you see how. So the file that I'm going to copy here is text phase one dot out. So I'm going to be plotting only from one file. I'm going to be plotting inverse for figures. I'm not going to be plotting. I can plot both. I will do both. I will plot first the inverse for figures because those are the ones that I show you. And the single crystal file is in the folder example 2 FCC, and it was called FCC.6, I think. And I'm going to be plotting. I'm going to just plot one pole, and those poles really correspond to the axis 001, because when you plot inverse for figures, you plot an axis of the sample. You don't plot a crystal. You don't plot a crystal direction. Let's say here we go again. Collate, compression. You probably can do it from yours, but there is a number missing here. Number of crystal poles to read is 1, and I mean I deleted something inadvertently. That's why it was not working. So it asks for how many poles you are going to be putting here. In this case, only one, and that is why it was not working. It should have worked also in the other one. No? No, now it is not going to be correct, but I'm going to be moving the poly.in I'm going to be moving it to the root directory of VPSC, and it should work. It should work. Okay, here we go. So it asks you to enter the settings or to choose. So I enter in 0 to use the default settings, and then you remember you do start new plot here. It opens new plot, and then you load the file that Pole created, which is compression.plt. Voila. That's what you get. What I suggest is that if you have the capability to plot the activity file, because I don't have something here that it will take me too long to use my software. If you want to plot the activity file or the stress strain, going back to the stress strain, there was a question yesterday of what is in the stress strain file, and I'm going to show that, and I also wanted to talk to you about the deviations. The stress strain file, I showed it yesterday, but it has the von Mises strain accumulated, the von Mises stress, then the strain components accumulated as a function of deformation. And because in this case we cannot calculate the Cauchy stress, it has the deviatoric stress components. And then temperature and time, which are part of the information. And this is the accumulated plastic work rate. Two definitions for the accumulated plastic work rate. But the file that I wanted to mention you about is the stress strain. This one, stress strain stats dot out, stats dot out. These are the standard deviations. These are the standard deviations in the components of stress and strain. So, as I said, there are five components that are independent, and these components we are going to see this representation, how we define those five components. We are going to see that later today. But you can calculate the standard deviation among all the grains, and that gives you an idea of how if you have a very narrow distribution in the strain and a larger distribution in the stress, it means that you are closer to the upper bound. You are closer to the Taylor problem. The other way around, if you have a large deviation in strain, but the stresses have a narrow distribution, then you are closer to the Sachs bound. And here, as you can see, the deviations in all the components of the strain rate from 1 to 5 are much smaller than the deviations of all the components of stress. So that already gives you an idea of how you are accommodating the formation and what the systems are doing. These are useful information to see how the assumption that you use for the interaction is working as far as distributing the strain among the grains. I wanted to show you what happens if you plot pole figures instead of inverse pole figures. What you have in when you do tension in an FCC that starts from a random one, you should get a texture with cylindrical symmetry for all the poles. So that's what we are going to be plotting now. Now the way I do this is I picked the Miller indices from one of these storage that is below. I mean, this is not read. These lines are not read by the code, but I keep them as to just cut and paste. So I'm going to be plotting the 100, 110, and 111 poles for this texture. I I need to put here 3 because I'm going to be plotting three poles, 0 for the pole figure, and the texture file is the same. So save the file. So now it is asking me to choose what is the order of the axis, the sample axis, 1 to the right, 2 on top, and 3 at the center. I'm going to choose the option of no symmetry, 0. going to plot them with new plot. And this is what you get. So you get cylindrically symmetric textures for all the components, and that is consistent with what I showed before. With what I showed before, where you saw that, or what you got before, there is a component where the tensile axis, which is the axis 3, where the axis 3, the 0, 0, 1, is aligned with the 1, 1, 1, and it is aligned with the 1, 0, 0. So if you look at the 1, 0, 0, these are the poles 1, 0, 0. They have a component of in the direction, this was tension. We are looking at compression. In compression we had this one. So it's not that. We had this one. So we did compression. So the 101, the 101 should we be aligned with the axis 3, which is what you see here. The 101 is aligned with the axis 3 plus something else. Okay, and if you do the same process for the tensile curves, you are going to see that they are centrosymmetric, but the 100 is going to be aligned with the direction 3, and the 111 is also going to be aligned with the direction 3.
You just said that 111 is also aligned with direction 3.
No, I made a mistake because I was referring to tension, but what I ran was compression. So in reality, only the 101, the 101 is aligned with the axis 001, with the direction 3. Only that.
And in the pole figure, when we look at it, that 111 is like a donut.
Correct. It has a cylindrical symmetry. Yes.
And from this, we can tell at what angle to the loading to the the axis of the sample.
Yes.
The 111 is oriented.
Yes, correct. If you these dots here, the dots there are the center of the cells in which I divide the pole figure, and those dots are really correspond to intervals of 10 degrees. So it's 85, 75, 65, etc. up to the center. So this you come from 0 here. You come from 0 towards 90. And they are every 5 degrees, roughly, because it is not exactly a division in angles, but a division in the cosine of the angle. You can do both. One is called a stereographic projection, the other is called an equal area projection, and I use the stereographic projection for doing this. Sorry, the equal area projection. The equal area projection means that elements that have the same area means that elements that have the same area will appear with the same area in the projection, and the stereographic distorts a bit the pole figure. So you have both options in pole A for plotting, but I usually pick equal area. The next problem that we are going to be looking at is the rolling of an FCC polycrystal, and in this example we will introduce several of the VPSC capabilities, and those are the capability of enforcing a monotonic deformation history, which is the same as we did for tension and compression, or a non-monotonic deformation history, which usually the applications that we have used, that non-monotonic comes from a finite element code. You pick the history of the formation of an element in a finite element code that you obtain with a J2 criterion or some continuum criterion, the deformation, and then you enter that history of velocity gradient into the VPSC code, and that gives you what would be the texture of that in that particular element. So you can get values of local texture in your piece, the piece that you are simulating, of local texture, internal stresses, etc. by doing it that way. The other is the capability of running several processes in sequence to calculate the rolling components, the yield locus of the polycrystal, the Lanford coefficients, and the directional Young modulus. So all of these capabilities will be demonstrated in this exercise. And in particular, if you look at this, this is a cup formed by drawing, pretty much the same as you use for producing the aluminum cans for beverage. Now, I like to mention and notice that when you do deep drawing, you have these undulations which are called earring in the piece. Okay, that comes from the texture of your roll sheet, because you start from a roll sheet, you punch it, and then you get, well, it's a bit you start from a roll sheet, you cut the disc, you punch the disc, you get these shapes. Well, in the case of the aluminum cans that are used for soda or for beer or for many beverages, this is a multi-million dollar industry. In the world, now about 500 million cans are produced every day. So 500 million cans per day, which means that improving the material that you use in the processes means a lot of money. One of the things that they have managed to do with those processes is that the aluminum that they use is such that the cans are thinner and thinner. The thickness is really a hundred of a millimeter or so. So it's really incredibly difficult to get that when you are producing those cans. Usually, the punch time for producing those cans is 1/3 of a second. So it takes 1/3 of a second to produce each of those cans, and they produce them by the thousands per minute, which means that two things. If you don't have the right material and they start ripping the aluminum, they have to stop the chain, and they have to figure out what's going on and change the process. But any stoppage, it means money, because you stop producing while the train is not working. The other thing is, if you can use material that is very thin, you reduce the amount of material that you need, so it costs less each of the cans. And finally, this effect, the earring, when you produce the can, there is always some amount of earring, so they have to cut around and throw away what is left. Now that means that you're throwing away part of the material that you use. So if you can eliminate this or make it really minimum, you are also improving your cost, because you're not throwing away material. So the way to do that is to tailor the texture and get textures that are as isotropic in the plane of the roll sheet as possible. So that is one way. With alloying properly, then you optimize the ductility of the product, so it is not going to break. So the Lanford coefficient in particular will give us a measure of how bad this process is. I'm going to define it. So how bad this earring process is, that gives you an idea. And we'll move to the next one. So I'm talking about rolling. In reality, what I'm going to be simulating here, but is practically the same, is plane strain process. So we simulate plane strain deformation of an initially random FCC polycrystal. Once again, we are going to use the 110, 111 sleep mode. We are going to deform to 100%, which is 63% reduction in rolling. We are going to use now a Voce hardening law that is linearly increasing. So the Voce law, we are going to make theta 0 and theta 1 equal to 1. So you start at tau 0 here, and by making theta 0 and theta 1 equal to 1, tau 0 is also equal to 1. You can give any value. Now we have a hardening material. The conditions is we are going to be imposing all strain components, all velocity gradient components, and compression in the direction 3, and extension in the direction 1, and the transverse direction doesn't change. So that is, when you roll the material, it stretches in one direction and compresses in the other, but it doesn't change in this direction. So that is the formation mode. And once again, we impose the component 3, we go in steps of 2%. So this is the interesting part that has all those cases that I mentioned before. The file VPSC18 will have this appearance. First, so we are going to switch on. One means yes, calculate cubic components. This will calculate the FCC rolling components. If we put 1 here, if you put 0, there is no calculation of rolling components. Now, we are going to run 3 processes now in sequence. These processes are run in sequence by the code. So the first process is identified with 0. 0 is monotonic strain path, and so we are going to run this FCC rolling file, which is the one that I showed before, this rolling file. Then we are going to calculate the polycrystal yield surface at the end. You can do that also in intermediate parts of the process. And of that yield surface, we are going to, because it is a 2-dimensional thing and we have 5 independent components, we have to say which components we are going to plot. So the usual components are the components 1 and 2. And 1 and 2 refer to this convention that we use inside the code, this convention to represent the stress vector. Sigma 1, sigma 2, sigma 3, sigma 4, sigma 6. Sigma 1 is sigma 2, 2 minus sigma 1, 1 over square root rho, 2 sigma 3, 3 minus sigma 2, 2 minus sigma 1, 1 over square root 6, and square root of the shear stress. Okay, we are going to plot this component against this component. I'll tell you in a moment why that is the case. The thing is, you are familiar with the Voigt convention to represent tensors, where you contract 2 indices into one index. The problem with the Voigt convention is that, yes, you define things like this: sigma 1 is sigma 1, 1, sigma 2 is sigma 2, 2, so on and so forth. For one thing, because the plastic work has to be consistent, whether you represent it as a tensor or as a vector like this in Voigt notation, then you need to add factors of 2 when you do the product of sigma times epsilon. You need to add factors of 2 to this definition of the strain or the strain rate. So that is not good. When you have to do multiplications of tensors, but using the Voigt convention, you also have to add factors of 2 in different components because in order to compensate. And when you do matrix inversion, when you do the inverse of a tensor, but you invert the matrix represented with the Voigt notation, you have factors 1/2 and factors 1/4 that affect different terms. So it is really a messy convention, the Voigt convention. This convention, which is a convention that we use inside the VPSC, eliminates all those issues, and besides, it has the great advantage that the first 5 components are deviatoric, and the last component is proportional to the pressure. It's the sum of the stress, the trace of the stress tensor. So the pressure in the dilatation go into the 6 components. So if we are working with a viscoplastic problem where things don't depend on the pressure and there is no dilatation, then this convention is particularly useful because we only work with only the first 5 components, and we ignore the sixth one when we do that representation. Okay, so what are these components with respect to the ones that you are accustomed to see? You are probably accustomed to see representations of the yield surface that look like this. That look like this is sigma 1, 1, sigma 2, 2, sigma 3, 3. Now, the component sigma 1 is essentially a component in this direction, is this axis. Sigma 1 is sigma 2, 2 minus sigma 1, 1. It goes in this direction. And sigma 2, which is 2 sigma 3, 3 minus sigma 1, 1 minus sigma 2, 2, goes in that direction. So that is how these components are disposed with respect to what you usually see when you plot yield surfaces. This is really a projection. I'm only going to work with sigma 1, 1, sigma 2, 2, sigma 3, 3. I'm ignoring the shears in this plot. Now, if this is a reference system, and you say that your yield surface Your yield surface is a surface such that every point in the yield surface will produce plastic deformation of the material. Um, uh, just believe me that this line along the 111 direction corresponds to the pressure. This line corresponds to the pressure. So if you project this axis, the axis sigma 11, sigma 22, and sigma 33 into this plane, you get that those triangles separated by 120 degrees. And here, this is now sigma 1, that component, and this becomes sigma 2, the components that I defined over there. So your yield surface is going to be something that is drawn in this plane. It's a projection into this plane. So the first two components, sigma 1 and sigma 2, with respect to the sigma 11, sigma 22, and sigma 33, are disposed in that way. And one more thing, some of the math of that problem, which is called the B-basis representation, is described. You can represent these symmetric tensors using the B basis. You can represent tensors a linear combination of these 3 by 3 matrices. That is called the B basis, and the components refer to the components in this B basis, and they have that property. I mean, if you are interested, I can give you more information, but essentially that's where this basis is and these components are coming from. What comes next will be the explanation of the landfall coefficient and the calculation of yield surfaces that propose this basis were some German guys by the name of Rederich, and this German guy by the name of Rederich. He was interested in the eigen frequencies of resonance in cubic materials, and so he picked this basis because the normal frequencies of resonance are consistent with those matrices that I showed there. And he called them B tensors. But they are, if you want to know more, they are the eigen. If you diagonalize the stiffness tensor, the solution, the eigenvalues are, if I remember it correctly, are sigma 11 minus sigma, or sigma 22 minus sigma 11 over 2, and sigma 44, and I think that yes, 2 sigma 33 minus C 11 minus C22, something like that. Anyway, the B bases are the eigentensors of the stiffness tensor of a cubic material, and the eigenvalues are these values that, and so it makes it much more sense to work in that basis, because those are the natural resonant frequencies in cubic crystals. And they call them B, and then that's what was adopted, no, from then on.